Back to another video, guys. You're on A-level maths and we're doing differentiation rules proofs. So this is the last one about the sum and the difference rule, and I'm pretty sure that after watching all those 3 previous videos you can do that, I bet. So let's try to do finally. For those who are new here, don't forget to subscribe and smash those like buttons and bell notification. So let's try to do it together. All right, so we have two functions, gx and hx. So let's denote this function as f from x. Or to simply test the first specified case. What if h from x is just a constant? So this is a specific case. In this case, we'll have gx plus c, right? And we're taking prime. What we expect to have. On the right side, we expect to have just simply g prime. Okay, let's test it. I just drop quickly allowed for x, y set, and let's pretend that we have f. So in our case, it's just simply gx function. And let's pretend that we use transformation. We move it c units up, and this is our transform function, which looks like fx. Okay, in our case, this is fx, which is equal to g from x and plus c. What do you think, guys? Transformation, vertical transformation, doesn't change the gradient of the function. In other words, it doesn't change the shape of the function. So that means, obviously, the prime of gx plus c is going to be equal to g prime. And that means, just by definition, is going to be g prime from x and plus c prime, which is simply 0. Okay, we've done a private case, but let's have a look more generally. So what I denoted fx, capital Fx, as the resultant function, is the sum of gx and hx. So we're gonna prove that f prime from x is going to be g prime from x and h prime from x. What we're gonna do, we just go by definition, using differentiation from first principles. We're taking the limits when h is very small of the fraction. So here we take capital F, so I just rewrite in our terms capital F and capital F. So that's why we need to plug x plus h arguments inside, but it, in other words, means that we need to plug x plus h and x plus h inside arguments of each partial function. So that's why we'll get gx plus h and x plus h. In this case, h is the function, while h inside, this is the constant horizontal step, right? When actually h is very small. So this is that variable that, or that constant that very close to 0 tends to 0. So don't mess up, okay? And you need to take away g from x, and you need to take away h from x. So that's how normally we work. Okay, so f prime in our case, and now I just group a little bit differently. So I will group g with a g function, but probably with another argument. So it's going to be gx plus h. I take away gx, and I'm dividing by h, okay? And because limit of the fraction, when you actually have the top one, can be separated, so you can represent your fraction as like this. And here you'll have x plus h minus h from x over h, okay? Those h, one more time, just probably denote this h is different from that h. So everywhere, h is completely different from the argument h that you plug in. So I just denote that h has the blue one, okay? And finally, what we'll have that if I squeeze that, just simply lift it up, I will have the following. So I first squeeze. That f prime is gonna be equal to limit of the first fraction, limit of the first fraction, gx plus h minus gx over h, and plus the limit of another fraction which contains those h functions. So that's why I just changed the color, h and h, and then I use normal yellow one. So x plus h minus x, h from x. Okay, and what do you think about the first one is g prime by definition, and the second one is going to be h prime by definition. So that's why finally we actually proved that right now what we have right there is we have on the right side both primes of each particular function. And left hand side, if I go back to our original notation for g and x, I'll get g from x plus h from x and prime. So that's why the left hand side equals to the right hand side, and it's done. So guys, hope you like those proofs. I think that if you are asked to do that, you can do. And don't forget, always use definition from first principles, because every single proof about how derivatives is taken technically, that's okay. But how to prove that? Use differentiation from first principles. Make sure you also watch all the previous videos, and see you next time. And don't forget to visit A-levels, Zillion's classes. Peace.